Okay, welcome everyone. My name is Maciej Zytowski. I'm from Pawsey Supercomputing Centre, and we are meeting here today to discuss a couple of projects from our PaCER program. And before we start, I would like to acknowledge the traditional custodians of the country throughout Australia, and their connections to land, sea, and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Welcome to the event. I would like to give you a very short, brief overview of what PaCER program is. Pawsey Centre for Extreme-scale Readiness, PaCER, is Pawsey's response to the unique opportunity to help researchers achieve superior scale on our next generation supercomputer. The focus of the PaCER program is on both extreme scale research, so algorithm design, code optimization, application and workflow readiness, and using the computational infrastructure to facilitate research for producing world-class scientific outcomes. PaCER provides researchers with an opportunity to optimize their codes and workflows suitable for next generation supercomputers and Setonics, Pawsey's next supercomputer. It is designed as a minimum 3-year partnership for collaboration with Pawsey and HPC vendors by providing early access to supercomputing tools and infrastructure, training, exclusive hackathons focused on HPC performance at scale. PaCER projects are also provided with co-funding for PhD or postdoctoral positions to work on technical aspects of their projects and build supercomputing expertise within their groups. 10 research projects were successfully granted access to the first Pawsey Centre for Extreme-scale Readiness PaCER program, establishing Australia's research platform for extreme-scale computing. There are some amazing statistics behind PaCER. We have 10 projects, but 18 institutions involved, including US national labs and industry partners. We have 70 plus researchers involved in the project, 10 plus Pawsey supercomputing experts supporting projects, and 10 plus new positions will be created to support that effort. Pawsey is hosting a series of seminars throughout June, showcasing the first cohort of PaCER research projects. So this is the second seminar in the series, and it focuses on the computational fluid dynamics projects at PaCER. Before we start with the presentations, before I give the floor to our great presenters, I would like to remind about the format of this meeting. So today's presentations will go for around 15 minutes, and after that we'll have a Q&A session to allow all the participants to ask questions. And for questions, please use the chat available in Zoom. Post your questions there. We might be able to answer. So Pawsey staff or presenters might be able to answer some of your questions during the session. For those that will not be yet answered, we'll try to go back and look at them during the Q&A session at the end of our today's meeting. With that, let's get straight into presentations. We have 3 talks scheduled for today. I will introduce each of the presenter before their talks. And first, it's my great pleasure to introduce Professor Richard Sandberg. Richard Sandberg is chair of computational mechanics in the Department of Mechanical Engineering at the University of Melbourne. His main interest is in high fidelity simulations of turbulent flows and the associated noise generation to gain physical understanding of flow and noise mechanisms. He is also pursuing novel machine learning approaches to improve low order models. He got a PhD in aerospace engineering. Prior to joining the University of Melbourne, he was a professor of fluid dynamics and aeroacoustics in the Aerodynamics and Flight Mechanics Research Group at the University of Southampton and headed the UK Turbines Consortium. He was awarded the Vesky Innovation Fellowship and granted an Australian Research Council Future Fellowship for 2020-2023. Richard, the stage is yours.
All right, thank you, Maciej, for the introduction. Thanks for the invitation, and thanks everyone for joining. So I'm going to talk about our project, which is entitled Towards Exascale Simulations of Efficient Low Emission Gas Turbines, or GTX. And it's a joint effort. It's a collaboration between University of Melbourne, which I'm leading the effort of, and then UNSW with Professor Evatt, who is going to talk after me, and we've got GE as an industry partner as well, and they're providing two experts, one on turbomachinery, one on combustion, to support the project. And I really should add also to that list, of course, the Pawsey Centre. So I'm just looking at my slide here and seeing that there is just one logo missing. So obviously, this is a joint effort with Pawsey as well, and Alexis is kind of working with us already on the turbomachinery part. Okay, so let's get started. And why gas turbines? That's really the first question. And gas turbines play an important role, and we believe will continue to play an important role in many aspects. First of all, a lot of electricity is produced with gas turbines. In Australia, it's more than 20% that's produced with GTs. And of course, if you fly on an airplane, the likelihood of it being powered by a gas turbine is very high, probably 99% or higher. So there's a huge installed base of gas turbines globally, and even very small increases in gas turbine efficiency will therefore result in very significant savings of order hundreds of millions of dollars or more, and of course the associated reduced emissions. And we believe these gas turbines will remain essential to our economies as they are very efficient. You can get more than 64% efficiency nowadays in combined cycle. They're pretty robust and compact, but they're also able to absorb intermittency of renewable sources pretty well. So if you have a bunch of solar, PV, and wind resources, but they kind of don't produce very much, at some point you just start up the gas turbine very quickly, and you can kind of even out the fluctuations. And longer term, there's probably a need for gas turbines to also be capable of burning carbon-free fuels. For example, hydrogen, and this is something that Evatt will talk about when he talks about his part of the project. And of course, for long-distance aviation, we don't really see any alternatives to gas turbines as a propulsion option, just because the energy density is so high, and you can't get that from batteries, not the ones we have now, and well, who knows whether we can ever get that from a battery. Okay, so that's the why. Now, just a very brief primer on what are the essential components of a gas turbine, and I've put up this schematic here. In this yellow box, we basically have a compressor, and its role is to increase the pressure of the ingested air because we want to burn our fuel at a high pressure. Now, the big challenge for the compressor is to achieve a very high pressure ratio, and we're talking increasing the pressure by a factor of 40, 50, 60 in the latest generations of engines. And we want to achieve that without having any flow separation on these blades. So it's a huge challenge because the flow actually wants to go the other way. And it's a very large challenge to design these compressors to do what they're doing. The next main component is the combustor, and this is really what Evatt is going to talk about later. Here the fuel is going to be mixed with that high pressure air, and you want to do that with producing the least amount of emissions while avoiding all kinds of instabilities. And again, Evatt will talk more about that. And then we've got the turbine, which sits at the back end of the engine, and that really is there to extract the energy from that hot gas coming from the combustor. And it's going to not only drive the compressor, but it's hopefully having excess energy that can then be used to drive a generator to produce electricity, or you could have on an engine for an airplane, you would have some kind of propulsion device, a fan that produces all the thrust. And here the challenge is we want to do this at as high efficiency as possible, because the higher the efficiency of the turbine, the more usable work we actually have that we can use for propulsion or energy production. But what comes out of the combustor is very hot, and it's typically hotter than the melting temperature of our metals that are used in these turbine blades. So we really need to understand what's going on there to design blades that are actually going to survive. Okay, so how does high performance computing help in all of this? Well, if we look at how these engines are designed, traditionally people looked at correlation-based approaches, but they're really, they've come to the end of what they can do with those correlation-based approaches. If we want to further improve efficiency, we need more detailed prediction capability. Also, experiments and testing is incredibly expensive because all of this happens at very high temperatures, high pressures, etc. It's very hard to measure, so we can't get complete information of what's going on inside of the engine. So this is why we kind of look at computational fluid dynamics, which can provide us with much more detail. Now, unfortunately, the flow is very complex, and current models for turbulence aren't really accurate enough. So we have to try to make sure that we can resolve everything in great detail so that we can actually understand phenomena more accurately and exploit them. Now, why is this accuracy important? Well, it's very important because small errors in our prediction can have a huge impact. So a 2% error in the predicted metal temperature, for example, can have the blade life in the high pressure turbine. And also, if we can reduce the amount of cooling air that we need for a given machine, by just 1%, we can increase the efficiency of the entire system by 0.4%, which, given the overall consumption of fuel, is a huge number. So we need that accuracy. So how do we get this accuracy? Well, we get it by running something that is called a direct numerical simulation, where we don't use any modeling. We just try to resolve all the scales of motion that we have. And this is an example of a high pressure turbine blade, where we can see that there's a lot of different things going on, and there's a very wide range of scales. So we have large scale structures coming in, which are kind of disturbances coming from a combustor. But these scales, large scales, wrap around the leading edges of these blades. They interact with that leading edge, they stretch. Then we get acoustic waves, we get kind of vortex shedding. We go from kind of a smooth laminar flow to turbulent flow. So there's a lot going on here, and it's actually quite difficult to model. But with DNS, we can actually resolve all of these scales. Now, the issue is if we want to resolve all these scales, we need very, very fine grids, and we need to run our simulations over very many time steps. So at the end of the day, we end up with problems that have up to the 10 to the 16 degrees of freedom. Which is a lot. So that'll take us a few thousand years on a laptop. Luckily, we don't only have laptops, we do have bigger machines. But even on supercomputers, these cases can take weeks or even months. And this is for still simplified configurations. But despite all of this and the high cost, DNS provides a lot of value. First of all, we can get detailed physical insight, which then can be exploited by designers and others to improve the efficiency of engines. But we're also producing so-called gold standard data, so reliable data that we can use to develop more accurate models. And that's very important too. So I just want to give two quick examples on how previous DNS studies we've been able to run on large supercomputing systems have provided insights that really have been of value to turbine designers. And the one example is looking at a low pressure turbine. So this is the back end of a gas turbine where the pressure already has decreased a little bit. So they are not seeing as hot gas as the high pressure turbine. And here the question is, if we have a blade row next to another one, what's the gap between those blade rows? I'm not sure. Can you actually see my cursor? I hope you can. So the question is, what is the distance, the axial distance between two blades? And so we've run a few simulations where we varied that blade distance. You want to keep your machine as short as possible because that's going to decrease weight and it has rotor dynamics benefits. But the question is, if you make that gap very short, is that actually good from an efficiency standpoint? So we have two simulations. I'm just showing you a few snapshots here of what the flow looks like that goes through the blade passage of the aft blade. So we have a wake that comes from the previous blade and is ingested between the subsequent row of blades, and then it just goes through that passage, and you can see these wakes are very strongly stretched, and all these kind of turbulent structures, you can see them in various guises. There are long structures, there are very small structures. You've got a lot of stuff going on. So again, this is very hard to model, and we do need to rely on resolving these scales to actually faithfully represent what's going on here. So it's great to look at structures, but of course we want to look at things a little bit more rigorously. This is basically just comparing how much turbulence kinetic energy production do we get in these different cases. And so I've got a SG case, which is my small gap case, and an LG case, which is a large gap. And these contours are basically the production of turbulence kinetic energy. So how much turbulence is produced. And the message really is, if we have a small gap, we produce more turbulence kinetic energy simply because the energy of the incoming wake is still higher, the amplitude of the fluctuations. And basically to look at this in a more quantitative way, I've got these bar charts here. And if we just kind of focus on these kind of bars where we have this blue circle, we can see that the small gap case produces more loss than the large gap case. And that's simply because we have more turbulence kinetic energy that's produced, but it also has to dissipate or is kind of converted into heat, which is lost. So what these simulations told us is that if you place these blades very closely together, maybe your machine becomes shorter, but you actually are generating more loss and more entropy. And that's not good, because obviously that reduces the efficiency. And for this little change alone, we get a 0.25% reduction in efficiency, which is quite large in the turbine world. So this is one example of how these high fidelity simulations can help us. And here's another example where we're looking at now the high pressure turbine. And this is the case that I showed that movie from before. We've got this very complex flow field. And of course, we care about how much heat is going to go to the blades. That's really crucial. So we ran a campaign of different inflow conditions, different length scales of the structures coming from a model combustor, and different amplitudes of these structures. And I just want to show these two images here, which look very different. So this is looking at a turbine blade from the front, and seeing these structures that wrap around that leading edge. And we can see with different turbulence intensities here at a given length scale, we're seeing very different behavior of the flow. And that all boils down to ultimately, if I look at my heat transfer to the blade, so this is this graph, it's heat transfer over the surface. My heat transfer changes dramatically if I'm actually putting in different structures. If the structures become very large and more energetic, my heat transfer goes through the roof. And of course, the designer needs to know that, because they have to design the cooling system to protect that blade. Okay, so this is what these kind of cases can tell us. Now, the challenge going forward really is to add more realism. Everything I've shown here has been done on very simplified geometries. And we've assumed that the turbine blade is perfectly smooth and that we don't have cooling holes. But this image here is an image of a real turbine blade, and you can see there's lots of cooling holes that blow kind of cool stream of or cooler stream of air over the blade to protect it from the hot gases coming from the combustion chamber. But also in service, engines will kind of see some kind of fouling and buildup of residues and erode. And so we get pretty rough surfaces. And this is really something we would like to include in our simulations, because it does really change how the flow behaves on the blades and how the heat transfer changes. So we can kind of do this already. We can put a rough surface onto a blade. This is an example here. But we can't simulate it yet because we don't have a computer that's big enough or a code that actually scales to those size problems. Because once we want to resolve all these details of this rough surface on top of all the small scales of turbulence, we really need a lot of degrees of freedom to look at this problem. And this is really why we need to get ready for extreme scale or exascale. So that leads me to this PaCER project, which is all about getting the code ready to do this kind of work, and then actually doing the problem that I've just mentioned. So work package 1 of this project is porting, optimizing our in-house code to the AMD CPU GPU architecture. The second work package is actually Evatt's part of the project, which you will talk about in a second, which is another code. And then we've got 2 grand challenge problems, one for each code. So on our Hipstar code for turbo machinery, what we want to do is, in terms of a grand challenge problem, we want to simulate the flow over a rough turbine blade. So we've already generated that roughness on a blade, and we can kind of run subscale preliminary calculations on this, but not at real engine operating conditions. We just need the code to scale better, be faster, and also we need a system that allows us to do that. Okay, and once we've generated data from these grand challenge problem, we also hope to use some of that data to develop models using novel sophisticated machine learning techniques, because those models will then be quite useful for our industry collaborators. Okay, so just a very quick introduction to one of the codes, Hipstar, which we are going to use for the turbo machinery work. So it's a very thoroughly validated in-house code. We've applied it to a number of turbo machinery problems already, but we use it for other things too. We look at air acoustics, so noise generated by turbine blades or wind turbine blades, or just airfoils, so spoilers on aircraft. It's a fairly flexible code. It's multi-block. We've got a sliding mesh technique and an overset technique, so we can actually do quite a few things with it by now. We've added buoyancy effects, and in particular, we've added an immersed boundary technique that is a high-order immersed boundary technique that now lets us do things like the roughness that I've just talked about, but also it allows us to do flexible structures. So this is an example of a moving plate, which we can do with this immersed boundary. And finally, it's already optimized for both CPU and GPU. We're running it on Summit, on large number of GPUs. So we've gone to cases up to 50 billion grid points. This is not a routine case. This is more for testing, but routinely we're running of the order of 1 to 5 billion grid points on GPU systems.
Your time is over.
Okay, well, that's my last slide. So I can just put it up here and say, these are the next steps that we're going to run through. So we've got to port or go from OpenACC, which is our current program model, to OpenMP. And then we're going to look at whether we can port some of the compute intense kernels to HIP as well for the AMD. And we've got to look at some load balance issues, etc. And this is why we have this multi-step approach of increasing slowly the complexity of the cases so that we can exercise different parts of the code and look at those load imbalance issues. But that's all I wanted to say. So thank you very much.
Thank you very much for this great talk. I'll just remind, because we had a couple of participants joining during your talk, that you can all ask questions using chat, Zoom chat, and we will come back to those, or at the end of today's session, or some of those questions might be also answered by us or by presenters in the chat. Now it is my great pleasure to introduce our next speaker, Professor Evatt Hawkes. Evatt Hawkes is a professor at the University of New South Wales in Sydney. His group applies high-fidelity computational fluid dynamics models to turbulent reacting flows that underpin the performance of combustion and solar energy systems. His work aims to make fundamental and practical advances in problems of industrial relevance in transportation, power generation, and other energy systems. Prior to joining University of New South Wales, Evatt graduated from the University of Cambridge and worked as a postdoc at the Combustion Research Facility of Sandia National Laboratories in US. He serves as Associate Editor of Proceedings of the Combustion Institute, as Advisory Editor of Flow, Turbulence, and Combustion, and regularly serves as a co-chair for the Turbulent Flames Colloquium at the International Symposia on Combustion. Evatt was awarded an Australian Research Council Future Fellowship and also elected as one of the inaugural class of fellows of the Combustion Institute. Evatt, The stage is yours.
Thanks for the introduction. You've just heard from Richard about the turbomachinery part of the problem. I'm here to talk about the combustion part, in particular our part of the project to look at hydrogen combustion for gas turbines. Our team at UNSW includes myself and 3 postdocs, Armin Ware-Fritz, Harshad Ranadiv and Deepak Dalakoti. So why are we looking at hydrogen now? The main reason, of course, is that we need to decarbonise the economy, and this needs to happen quickly and globally. Although Australia's been sort of lagging a bit, I think people are now finally realising what a massive opportunity this is for us. The costs of solar electricity generation have really fallen sharply and seem to be continuing to fall. And we have a very large land area with massive insulation, so that we can do this pretty much as cheaply as anyone can. Not all countries can actually make enough renewable electricity on their own, which means they're going to need to import it. So there's an opportunity for us to sell it to them as long as we can get it into a form that we can export, such as hydrogen. Hydrogen would also help us domestically to reduce the amount of overbuild for other types of energy storage, and it finally would help us decarbonise difficult sectors such as in heavy industry like steel and aluminium. So one of the things you need for a hydrogen economy to work is a way to convert the hydrogen back into electricity. And most people associate hydrogen with a fuel cell. However, if you look at the numbers, a combined cycle gas turbine, which is basically a gas turbine with a steam turbine tucked on the back of it, is actually a lot better. It's more efficient, it costs less, it occupies orders of magnitude less space, and it can also run on other fuels if it needs to, or fuels containing impurities. So there's quite a compelling use case for gas turbines. And I'll mention as well that when we get to decarbonising aviation, it is technically feasible to use hydrogen there as well, presuming we can store it in a high enough density form. So Richard talked a bit about some issues in turbomachinery, and I'll talk briefly about some issues in combustion, trying to keep this at a relatively high level. So first off, stationary turbines for electricity production use fuel lean combustion. That is, there's more air than is actually needed to complete the reaction. That's done in order to keep combustion temperatures low and therefore avoid emissions of NOx. To achieve that, you need to mix the fuel and air together before they enter the combustion chamber. As a result, that mixture is explosive, and so you need some way to stabilise the flame within the chamber. That's normally done by introducing a swirling flow pattern, which makes a sort of a low velocity region in the middle where the flame likes to stabilise. So with swirling premixed flame stabilisation, there's a few things that can go wrong that you need to avoid in design, and this video shows one of these things. This is a premixed flame of methane with air, which is stabilised on a swirling flow that comes from sort of a ring-shaped duct on the left here, with a solid centre body. In the design condition, the flame is stabilised on the right, where it's sort of conical shaped flame on the right here. However, as you can see in this video, sometimes this flame can propagate back inside the duct, which is called flashback. That's an off-design condition, which is very undesirable and can basically melt a bunch of things inside that mixing section. So it's not something you want to have happen. Other things can go wrong. For example, if you increase the velocity in the duct here, you can eventually get to a point where you can blow the flame out the right-hand side, like blowing out a candle. Another thing that can happen is that the flame can produce sound, and that sound can lock onto resonant modes of the combustion chamber, which leads to what's called a thermoacoustic combustion instability, which is another thing that can go wrong, and that can essentially shake the combustion chamber to bits, actually, if it's strong enough, and leading to bits of the combustor liner going through the turbo machinery, which is Richard's lovely turbo machinery gets destroyed in that process. Importantly, all of these things are influenced by the burning characteristics of the fuel, especially the burning speed, and hydrogen has very different characteristics from methane. So anything that you designed specifically for methane won't necessarily work for hydrogen. And the tool we're using in the PaCER project is the same type of approach that Richard has described, the direct numerical simulation approach. And Richard's given a nice introduction where basically this is a computational fluid dynamics model which needs to resolve the smallest continuum scales. And in practical flows, those small scales are very separated from the large scales, so that becomes a quite expensive, computationally expensive problem. In combustion applications, you need to additionally carry the chemical species concentrations and compute the reaction rates and so on. So it's a little bit more expensive for the same flow to do a reacting flow problem. The good point about DNS is that Richard really nicely outlined is once you have done it, then you have access to everything, which enables fundamental investigations really like no other technique. And as Richard said, another point is that you can then use the data to develop practically applicable models that you can actually use in industrial design. I always like to give this plot showing the cumulative floating point performance of the top 500 supercomputers over time. And as you can see, we've been on a pretty impressive trajectory, having beaten Moore's law significantly over the last 3 decades. Things have slowed a little bit recently, but we're still going at a fair clip that enables still significant progress, particularly in programs such as the PaCER program. With combustion DNS, of course, the increase in computational power has led to a corresponding increase in the scale and ambition of DNS runs. So we sort of started out with an example such as shown on the left here with quite weakly wrinkled flames with very idealized settings and 1 or 2 step chemistry. So now we're at the point where if you have decent CPU time allocation and good DNS code and obviously an interest to work on this problem, then you can start to do something that's, really looks like a real sort of laboratory scale flame. So this case on the far right is an example of that, one of the recent cases that we've done at Pawsey. The code we use for the PaCER is called S3D. It's like Richard's code. It's a compressible high order finite difference code. It solves the compressible Navier-Stokes partial differential equations, and different from Richard, in addition to that, we need to also compute a bunch of scalars which represent the combustion chemistry. It really is a very simple code, but its simplicity allows us to pay a lot of attention to small details that really make it fly on a supercomputer. There's a few versions of the code around, but the UNSW version, we've essentially refactored it a couple of times. We refactored essentially all of the compute heavy kernels in 2018, and then finally in 2020, we've refactored the entire code. And as you can see, that refactoring really reduced the cost a lot. Also of note here is the very good weak scaling performance, where a flat line here would represent perfect scaling. So some of the reasons for this good performance include a lot of hiding of communication, sort of memory bandwidth aware coding such as case blocking and so on, and above all very high levels of vectorization, which is quite important in combustion kernels due to heavy use of exponential log functions. We also have several strategies available for hybrid computing, and one of the objectives for the PaCER project will be to update those and incorporate them into the current UNSW version. Anyway, I just wanted to show one example of what we can do, and as PaCER hasn't yet started, I'm going to use a computation that we're carrying out at NCI under the Australian Leadership Computing Grant Program. I apologise for highlighting the composition, but this is the closest one that we have that what we'll be able to do in PaCER. This run is motivated by the fact that in high pressure turbine blades are now so good that we can start towards increasing the combustion temperatures, which increases the cycle efficiency. However, if we do that, and we do that with just a single stage combustion, which would be the traditional approach, we would result in too high emissions of oxides of nitrogen. So what we're looking at in this problem is an approach to inject a bit of additional fuel and air just before the high pressure turbine. And if we inject it very late, there's not enough time for the NOx to form so that we can achieve high temperature without increasing the NOx. This, however, leads to many questions because this is not a standard premixed type of flame. We're injecting the fuel mixture into an environment of hot products, so we don't know how that flame is stabilized, and also we don't know things like, for example, about how any NOx that might form there is formed. So to look at that in DNS, we picked a simple configuration of a cold premixed fuel air jet being injected into a hot crossflow, which is coming from the upstream lean premixed stage. I'll just give a few details. The domain is basically a cuboid. We use a relatively complete model of methane air combustion with the chemistry of the pollutant NOx. In terms of the simulation scale, there are about 9 billion grid points leading to about 10 to the 16 direct degrees of freedom. So the same order of magnitude as what Richard was mentioning. We're running this on about 18,000 processor cores, and this will be, this single run will require 24 million service units. We're going to generate a whole bunch of data, 4 petabytes, and we can't afford to store that, obviously. So actually a lot of that is going to be processed on the fly and thrown away. This is actually an interesting point because this is the first time that we've needed to do that. I guess going forwards, we'll be heading into more of a data limited era. So these calculations feature a jet in a crossflow, which is a complicated problem from the fluid dynamics perspective involving different types of vortical structures. We can have jet like shear layer vortices forming in the shear layer of the jet. We can have vortices that shed off the edges of the jet that are called wake vortices that sort of connect the boundary layer near the wall up to the jet. We also have what's called a counter-rotating vortex pair, which is that sort of eyeglasses type shape structure that you can see in the cross-section. And finally, we have near the wall boundary layer, we have what's called a horseshoe type of vortex. So what does this all mean for the flame? This is from a slice taken through the middle of the jet from one of these computations. And I'm showing here the hydroperoxyl radical, which is an important radical in autoignition chemistry. As you can see, the flame clearly stabilizes on sort of the downwind side, which is called the leeward side. This was not unexpected as some experiments in similar configurations have shown this. But what you can also see here, which hasn't been noticed before, is this sort of periodic ejections of the flame into sort of downwards and towards the wall. And we think that is probably also an important mechanism for the flame stabilization. Looking now at a cross-section through the jet, we see, and this is now being governed by the counter-rotating vortex pair. So it's one vortex is rotating anti-clockwise and one is rotating clockwise on this plot here. And hopefully, as you can see, the HO2 likes to generally live around the middle of this counter-rotating vortex pair. That is, any HO2 that's formed at the top or in the sides tends to get transported and dumped into the middle region. And again, that's a detail that's never been documented before, that we've seen first time on these runs. Finally, I'll show a plane that cuts across the jet. And as you can see here, we've got a sort of a periodic large-scale shedding of structures from the jet, which are associated with these wake vortices that have been previously observed in non-reacting flows. And so we can see that those wake vortices tend to pull with them reacting material, and then inside those vortices that provides an environment which is sort of free of losses, and those vortices end up being regions of high chemical activity. So we believe this is also a factor in the stabilization that also hasn't been previously documented. So in summary, even though this looks quite preliminary, we see some really interesting things in these data that will help inform understanding of how this flame is stabilized. And we're also hoping that it's a good data set that we'll be able to use to help our GE inform better combustion models that they can use to predict how these types of actually staged combustion systems behave. I'd like to finish with a presentation of a brief discussion of what we plan to achieve in the PaCER project. So scientifically, our objectives are first to understand how lean premixed hydrogen air flames are stabilized in swirling flows. And there are several important combustion characteristics of hydrogen that make us believe these are going to be quite different from natural gas flames. Second, we will use the data that we generate together with our industry partner GE to develop and demonstrate more practically applicable combustion models that don't require 25 million CPU hours per run. In terms of activities, the main things we're envisaging, apart from the simulations themselves, first to develop some standalone codes for auto generation of optimized code for the problem-dependent kernels, and those in combustion are essentially the combustion chemistry, the molecular transport properties, thermodynamics, and so on. And probably within those order generations, we will be able to adopt different options for hybrid computing. Second, we'll refactor the main problem-independent parts of the code to enable hybrid computing, with pragmas being the preferred approach for affordability reasons. And this will probably take into account what has already happened in the past with the same code for earlier refactoring under the Titan CAR and so on. Then we need to figure out what to do with all the vast amounts of data that we're going to produce. We need to figure out smart reductions of the data, because we obviously can't afford to, be storing 10 or 50 petabytes. We also think there may be several use cases where we can use lossy compression for some workflows. So we'll be investing in that. Finally, we'd like to improve our current machine learning analysis workflows that will help us in our practical combustion model development workflows. And I'll mention this is a difficult use case for machine learning, since the resulting models must fully respect many physical conservation laws, otherwise you're going to get garbage outcomes. So just finishing, thank you for your attention, and I'll leave you with this colourful fluid dynamics animation of a recent simulation at Pawsey.
Thank you very much, Evatt, for this interesting talk. I'll jump straight into the next presentation and introduce our next speaker, Dr. Christopher Leonardi. Christopher Leonardi is a senior lecturer in the School of Mechanical and Mining Engineering at the University of Queensland and an advanced Queensland Industry Research Fellow. Christopher is a mechanical engineer with a PhD in civil and computational engineering from Swansea University, UK, and research affiliate appointment in the Department of Civil and Environmental Engineering at the Massachusetts Institute of Technology. Leonardi's research is currently targeted at the development of large-scale numerical models, which can be used to provide insight into the complex characteristics of fluid-solid interactions in oil and gas reservoirs. Much of his work is undertaken in close collaboration with industry via the UQ Centre for Natural Gas. In addition to his academic pursuits, Christopher has over 5 years of consulting experience applying both computational and analytical techniques to solve problems in the mining and mechanical engineering disciplines. Christopher, the stage is yours.
Thanks, Marcek, and good afternoon, everyone, and good morning to those of you in WA. I'll just share my slides. You can see those all right, Marcek? Okay, great. So today I'll talk to you about MAPMOPS, which was the acronym we came up for Massively Parallel Models of Particle Suspensions, which we will work on as a part of the Pawsey PaCER scheme. So before I start, I'll just give a little bit of context for the research that we're undertaking here at UQ. And it is, as Marcek mentioned, about gas production, and in particular, here in Queensland, the production of methane from coal seams, known overseas as coal bed methane, or here in Australia as coal seam gas. And so there are a number of tensions around the industry at the moment. So there is a need for greater gas domestically within Australia, because currently most of the gas that is produced from CSG fields in Queensland is exported overseas by LNG, and that has had the effect of increasing the cost of gas for power generation here in Australia and for other feedstock type processes. There are economical, environmental, and political drivers for greater supply, but there are production challenges that the industry is facing as they continue the deployment of new wells, which is seeing the productivity of certain wells not being as high as hoped. And so with that reality, there are significant volumes of gas that are currently remaining trapped underground as 3C or contingent resources. So if one were to imagine the size of the CSG to LNG industry in Queensland right now, and it is significant, there is most probably a significantly sized industry locked underground in coal seams that are too tight or too difficult to produce from. And so the research that I am working on is aimed at trying to access those resources and have them converted to reserves, which can ultimately be produced. And so the areas that we're undertaking research, and the bulk of my research is computational, is ultimately focused on this big cog down at the bottom right-hand side, which is how can the permeability be enhanced in large volumes of coal, and how does this ultimately affect production estimates? Now, one of the ways that this is done, not just in coal seam gas, but in all forms of unconventional gas production, is via hydraulic fracturing. And this animation here shows a little schematic of what the hydraulic fracturing process looks like in some level of detail. What we see here is a cleat or fracture within a block of coal that has been opened up due to high pressure fluid injected into the subsurface and then injected with particles called proppant. And this proppant can be sand, it can be ceramic, it can be made of other things depending on the budget available and the technical requirement. But in general, the idea is that these fractures are impregnated with these particles, which when the fluid pressure is reduced, keep those cleats and fractures open to maintain and increase the permeability of the system. So if the subsurface is more permeable, there is a greater potential to produce gas from the reservoir and ultimately end up with a greater volume of gas for consumption or export. So this animation is actually based on some computational fluid and particle dynamics, where we're using the Lattice-Boltzmann method to resolve the fluid dynamics and the discrete element method to resolve the particle dynamics. And so what we have here is a high fidelity representation of the physical phenomena that are occurring deep within the underground reservoir. So whilst that, I believe that to be a nice animation, it's useful to talk about what we can actually do in a quantitative sense with this type of simulation. And what we have here is one example of what we can achieve with many small scale computations. Now I say small scale, but these are still of a size that requires high performance computing because of the number of time steps required and the resolution of the simulations in terms of number of grid points. So they're not certainly something we're running on laptops or desktop computers here. But as one example, we can look at the propensity for particle jamming within a fracture as the ratio of the particle size and fracture opening width varies, as the fluid properties vary, and as we add multi-physics effects such as electrostatics. And so on the left-hand side, we see a schematic of what this simulation might look like, where we inject some particles into a fracture. And then on the right-hand side, we see a summary of results which plots the probability of jamming occurring as a function of the solid volume fraction of particles in suspension. And so each one of these curves here represents a different configuration. And what's being tested here is the effect of electrostatic forces on the probability of jamming. And so as those curves move from the right-hand side to the left-hand side, we see that adding electrostatic forces to our simulation increases the chances of bonding of particles to the walls of our fracture, which narrows the aperture and greatly increases the probability of jamming at much lower solid volume fractions. Now, this is very useful information in terms of designing the type of problems that we would inject into the subsurface, but the number of simulations represented in this graph is significant. Each data point is based on an average of approximately 20 simulations, and each simulation would require hundreds of thousands or up to on the order of 1 million iterations. So the amount of work required to generate a plot like this is significant. And this is the kind of thing that we can do now. So in terms of MapMops, the work that we're going to do is, or the scientific problem is, high fidelity computations at physically meaningful length scales. And by what we mean by physically meaningful is something that we can directly compare to experimental data that is in the literature and larger configurations underground. And so what we really want to do is provide new fundamental knowledge on the nature of particle suspension transport and sedimentation in fractures and pores. So the technical and grand challenges are to develop a computational model of complex particle suspension. So that includes multiphysics, complex rheology, and particle kinematics that can be applied at the scale of hydraulic fracture slot experiments. And I'll show you what that looks like in just a little bit. However, the inclusion of the DEM, the particle dynamics, into the CFD simulation greatly reduces the consistency of data transfer patterns between iterations. And so we have variable amounts of data that need to be transferred between nodes in our HPC system, and that can become problematic for scalability very quickly and make load balancing quite challenging. Very quickly, the team is comprised of myself and Dr. Łukasz Laniewski-Volk and Dr. Travis Mitchell, both of whom are postdoctoral research fellows working within the group here at UQ. Łukasz originally from Poland and Travis originally from Brisbane. And then I'll just want to move to talk about the methods and their construction and what it means for the computational problem that we're facing. So as opposed to the work presented by Richard and Evatt so far today, we're using the Lattice-Boltzmann method for our description of fluid mechanics, and it's formulated quite differently to conventional CFD codes in that it's a mesoscopic kinetic model for fluid dynamics, where instead of discretizing some continuous equations, we actually have a model of particle transfer on a fixed grid, which with the right set of collision rules at the macroscopic level emerges to produce something that is analogous to Navier-Stokes hydrodynamics. And in the Lattice-Boltzmann method, we have this collision operator for each of the density functions that exist on the lattice nodes. And that's a completely local operation, which is very convenient computationally. But then after collision, we need to transfer information between nodes where we have particle distribution functions move from one node to their neighboring node. And so that's where the exchange of information between nodes occurs. The structured grid of the LBM facilitates simple data alignment and improves GPU bus saturation. So if you look at the schematic on the left-hand side, we show one representation of the way our data can be stored, where we would have an array of density 1 and an array of density 2, which then gets transferred or grouped for each Lattice-Boltzmann node and then processed for collision and then ultimately streaming. But the regular grid and the regularity of these data structures means that we can do a very good job of saturating the memory bus, certainly much better on GPU than it is on CPU. And the other thing to note is that SIMD operations can be handled very efficiently on GPU, as shown on the right-hand side, assuming there is only a reasonable degree of code branching, so not too much complexity or divergence in the computation when you have branching statements such as if statements. We have to use a lot of iterations to perform our computation. They're simple time steps, but we potentially need millions of them. And so at each time step, one of the challenges that we have is the transfer of memory between nodes, between CPUs, and then from RAM down to GPUs and back again. And so the key to success for our work is shielding this communication with useful computation, which is schematically shown on the right-hand side, where we try to ensure that we're doing useful work, the large volume of grunt work, whilst we have the communication of information via DMA back and forwards between CPUs and GPUs. Very briefly, TCLB is the open source code base originally developed by Łukasz and expanded on by others that we will be using for this research. The code gives the ability to develop specific models that are then compiled based on some other templates, so that each compiled application is for a specific set of physics and then either deployed on GPU or CPU. And the code's been used over the last almost 10 years, I think, for applications in porous media flow, thermal flows, ferromagnetics, waves, LES, aerodynamics, and then some biological flows as well. I mentioned already that the addition of the discrete element method makes things difficult in terms of communication patterns and load balancing. At the moment, we have 3 different particle codes coupled to TCLB, but they all base their parallelism on domain subdivision along the X, Y, and Z direction. So this is good because it fits well with the grid structure of the LBM, but it's bad because our computation is divided by space and not by the number of particles. And so if you imagine a sparse simulation where particles can move around freely, you can, via spatial decomposition, have very poor load balancing emerge as a result. So as a representative LBM DEM problem, this is flow of a particle suspension in a rough fracture, where it shows that this rough fracture generates hard to predict communication patterns which impede performance. And that's shown quantitatively here with these 2 graphs, the first being of weak scaling, where we see as we increase the number of particles and the number of lattice elements, that our weak scaling starts to deteriorate, where by the time we have 6 nodes here, we're down 25% on single processor performance. Although our strong scaling looks reasonably good as it stands, there's still a lot of work to do to improve the efficiency of the LBM DEM problem as we scale up to more and more cores. Okay, so just to summarize, the grand challenge, what we really want to do with the PaCER scheme is look at things that just happen at larger scales. So I've shown the value of lots of small scale simulations, but some things you just miss when you narrow your field of view. And so this is some results from an experimental slot analysis where some particles are injected into a narrow perspex slot, and their behavior over an hour and a half is observed. So the analog here is the injection of hydraulic fracturing particles into a vertical fracture. And so our challenge is to be able to replicate an experiment like this numerically, so that we can then start to investigate a whole range of things that cannot be interrogated experimentally. The effect of surface texture, different fluid formulations, rates of injection, things that are just intractable from an experimental point of view, if possible numerically, will open up a wide range of areas of research. So our goals, 4 billion lattice nodes on 150 GPUs with no less than 90% of single node speed, and then expanding on that to add 25 million particles and end up with no less than 50% of a single node speed. And so the 150 GPUs would correspond to an estimated 1 petaflop of performance. To achieve these, we'll collaborate with the Pawsey team on the HIP backend, CUDA MPI profiling, the optimization of our model definitions, and our communication pattern, improving the concurrency of GPU, CPU, DMA, and network operations across codes. And most importantly, as already mentioned by Richard and Evatt, is in situ processing, because the dumping of all of this data and the visualization of it will just not be possible. So that's all I had to say. Happy to take any other questions. And thank you for your attendance.
Thank you very much, Chris, for this interesting talk. We've seen a couple of questions being asked in the chat and also responded. I'm also aware that we are a little bit over time with our session. So I guess I wanted to allow also a little bit of discussion at the end, but before I'm also aware that some of you might decide to jump to some other meetings. So just briefly remind everyone that this is the second of a series of events that we are running around PaCER projects. There are two other that will happen on the 22nd of June, so next Tuesday, which will be looking at particle and molecular physics, and the 29th of June that will be covering radio astronomy projects. Registrations are now open for both events. I would like also to emphasize that PaCER is a truly collaborative project. Online seminars, some of the PaCER activities, trainings, hackathons will also be open to other researchers. So please watch that space. And if you are still keen to stay in the discussion for some questions, I actually have one question, so I wanted to ask. But before I do that, I also I saw that Karina posted to the chat that if you have some other questions or would like to be connected to our speakers, please send your email to pr@pawsey.org.au. And I wanted to very shortly ask about the challenges that you have with bringing your simulations to the new scale. All of your codes are already using HPC systems, are highly parallel, present great scalability, and are also using GPU architectures. There are some technical challenges that you have mentioned within PaCER related to, I don't know, transition from OpenACC to OpenMP or CUDA to HIP. But when you think of actually achieving that next scale of your science and simulations, what you feel will be more difficult? Those technical challenges of moving to some slightly different programming model, or actually a theoretical algorithmic challenges related to, for instance, stability of your models at scale with extreme number of cells and grid points?
So I'm happy to answer that one first. I think for us, the biggest challenge, I think the implementation stuff is all doable. It just takes time. But for us, I think algorithmically, it will be ensuring that we can have the coupled communication between fluids and particles, and then between nodes occur without affecting scalability as that number of nodes and GPUs increases. So ensuring that the communication that we have to do and the synchronization that is necessary between the solvers and the hardware is masked completely by other computations going on at the same time. Because if we have any significant synchronization bottleneck, then our scalability will fall away very rapidly, and we won't be able to take advantage of the size of the system that you're building there at Pawsey.
Yeah, maybe a comment from my side. I think for us, we see the challenge not so much in scaling up the problem. I think we're quite confident that just adding more nodes and having fast accelerators will allow us to go to bigger problem sizes. But I think the real challenges are the two things that both Evatt and Chris have mentioned. So one is data. We are going to produce more and more data, and we don't want to throw it out because we are producing it for a reason, right? And we want to mine it properly to really benefit or add value to these simulations. So this is definitely one of the aspects. And the other thing is something Chris mentioned, is that if we are resolving more and more smaller scales, it also means that the time scales reduce, and we have to run with explicit codes for many more iterations in time, so to say, and that's going to add to the wall time cost, and again also to the data generation cost, and those are really two things that I think we have to kind of get our heads around how we're going to deal with that. It's fine maybe over the next few years, but looking ahead maybe another decade, right? If we increase our problem size by a factor of 1,000, how are we going to deal with these things? So I think those are some of the real challenges that we have.
I'll just add to that as well. The perspective of what we've hit this problem with this Australian Leadership Computing grant that we got. So we got 50 million service units from NCI, and suddenly we found we're in the data limited regime. So in all previous runs that we've done, we have basically stored all of the data that we would need for any reasonable scientific workflow that we could imagine. And like the biggest data set amongst all the previous ones was 400 terabytes. And that's one of the ones we've done in the US. So we kind of knew that the data limited regime was coming, but I thought it was maybe 5 years away. But suddenly we're there now. And if we would write all of the data that we would normally write for these ALCG runs, we'd be left with about 10 to 15 petabytes, which we can't deal with. And one of the important things is that we sort of need to invert our workflow. So the previous workflow was do the run, store all the data, then come up with the scientific approaches to analyze the data and get the conclusions out. And, afterwards probably share it with other people who have different scientific questions that we didn't envisage. And now we're in a situation where we've got to throw most of the data away. So we've got to be cleverer about what storing what we need and maybe compressing some things. And, it was a surprise to me to get there already. So obviously with PaCER, it's going to be one of the key problems. So that worries me as well. It worries me more than scaling up the computation. As Richard said, I think we can do that. The data thing is more concerning to me because it affects the whole workflow essentially.
Okay, thank you. Oh, that's quite interesting. I think this is something that we see in a couple of other PaCER projects, especially the radio astronomy ones, where we have to probably be more. In future, we have to be aware that probably some of the data will be only able to look at this particular data set only once, because then we'll have to throw it away. There are a couple of approaches that we can have. We can the in situ visualization, which was mentioned, and the data compression discussion that we had in the chat, which is super important, that Jess mentioned. But machine learning was also mentioned in most of the talks, and I understand that this is probably going forward the way to a little bit reduce the, let's say, the service units or the cost of the simulations. You basically looking at optimization of parameters of your various simulations, but can also be in some cases used for to actually deal with the huge amounts of data that are being produced, and to understand what information that data brings for your simulation, I guess.
Yeah, thanks. Thanks for bringing that up. I was definitely going to mention that there should be, and probably is, some collaboration between the square kilometer array users of Pawsey and other researchers that are generating similar volumes of data. And yeah, there's quite a bit of work going on. Yeah, multiple. I guess I'm not as surprised as Evatt maybe was that the data volumes have exponentially increased to that point. It's something that I work in the oil and gas industry, and we've been dealing with that for the last decade, I'd say, where we got doing reservoir simulations, multiple node reservoir simulations, and storing the original subsurface geophysical data. We were up in that petabyte range, 8 or 10 years ago. So we've been looking at compression solutions for that. So yeah, interesting.
Oh, thank you all for participating, and especially our presenters for their talks, interesting talks, and all the participants. We hope to see you soon online and hopefully in person as well. Thank you all.